So in the Augmented Operator project, we have looked at the streamed AR. So that is that we have rendered content that's overlaid on the real world, and the rendered content is created somewhere offline and then streamed to the receiving device. And when doing this remote rendering, you will inevitably cause an extra time lag. And in this work package, we have looked at how to reduce this time lag by doing better prediction. And the way to do this prediction that we've studied is to model the trajectory of the camera or the headset or the hands of the operator. And these are modeled as continuous time representations in the form of splines. And when using splines, you can incorporate learned priors or explicit priors that tells you what is a likely movement and what is not a likely movement, and that will then improve the predictions.
Right, so hi, welcome. My name is Mikael, and I'm a PhD at Computer Vision Laboratory at CVL. My primary research is within visual odometry, and in the Augmented Operator project, we have been looking at predicting pose trajectories using a kind of regularized spline based on the KKS formulation. The reason why this is useful is because when you're working with visual odometry, or essentially any other way where you're estimating a pose trajectory, you're doing some kind of computation and you're adding this into the image, then if or as the cameras are moving, it takes time to compute the current pose, and you want to have an as low latency estimate as possible. So ideally, we want to know what the pose is at each instant, but there can be various computational delays or data transfer delays. And in this case, we may want to be able to predict where the cameras will be at the time that some computation has completed. And in order to work with this particular project then in Augmented Operator, right, we're looking at trying to assist an operator performing some kind of task. The idea is that a remote expert may be available to provide instructions, which are then followed by an on-site operator, which may lack specific knowledge or anything like that. So we needed a way to generate a data set for evaluating this, and we created one, which you can see in a couple of other videos. The way we did this was by using an actually existing augmented reality system called the Vive Index. Now, the nice thing about these things are that not only can we see through pass-through VR, but the system is convenient and simple to operate. So you can pretty much set up these base stations in any particular environment, and combined with the essentially markers on the hand controllers and the headset, we can get a very low latency estimate that is very accurate of the absolute pose of the head and the hands, or, well, these things, right? So we recorded a couple of sequences for this, both during a simulated Augmented Operator instruction operation, as well as a couple of experiments using various video games to show different kinds of motions. What we found is that it is relatively simple to predict the headset or the head's motion over time, likely because people do tend to hold their heads fairly stable, even if they are otherwise moving. And it's much more difficult to predict where the hands are. So fortunately, predicting where the head is corresponding to predicting where the gaze is, which means that predicting where the gaze is at is much simpler. And this is fortunate because this is what we need when working with, for example, augmented reality, right? Because the most important question is, from what perspective are you looking? And the system we developed works quite well. In the case of the headset, we were able to predict during the operator sequences with reasonable accuracy, roughly 200 milliseconds forward in time. That is to say, with less than 1 degree of error on average, as well as about less than 2 degrees with a 95% threshold, or in 95% of cases. So the results of this project are published in 2 different ways, both as a 3DV oral, so it's actually accepted for primary presentation at the conference, as well as my thesis, Visual Geometry in Principle and Practice. The key result is really this, or at least from a practical perspective, is a optimization framework, where essentially if you are working with post trajectories, you're optimizing these. This is a kind of simple way to optimize these post trajectories, which is available as open source online.